Our whole universe was in a hot, dense state that nearly 14 billion years ago expansion started. Wait, the earth began to cool, the autotrophs began to drool, Neanderthals developed tools, we built a wall. We built the pyramids, math, science, history, unraveling the mystery that all started with a big bang.
In the late 19th century, electric vehicles outsold any other type of vehicle. Their high cost, low speeds, and short range led to their decline. Now, interest in electric and other alternative fuel vehicles is at an increased high. Electric cars are pretty simple, and as you can see, they look no different than gasoline-fueled vehicles on the outside. Their differences can be found within the car. Their gasoline engines are replaced by an electric motor. The electric motor gets its power from a controller. The controller gets its power from an array of rechargeable batteries. So we're here at Nally BMW today, and we're going to talk about electric cars. There's three components that make up an electric vehicle: the electric storage unit, the control unit, and the propulsion unit. The main part of an electric car is the electric storage unit, and that's the electric battery. So the nice people at BMW wouldn't let me take apart the i3 to show you all the internal components. Instead, I created this little diagram over here to the right to show you how simple the actual technology is. Electricity turns the wheels independently while current is sent from the battery system. The power from the battery provides the motor the ability for the wheels to provide movement to the car. The voltage is controlled by the controller. The battery is actually what stores the energy to power the car. And simply, the charger is what recharges the battery. The battery is made up of lithium-ion batteries. It's the same thing that we use in our laptops. The problem with old technology was that it couldn't keep charged long enough, so cars weren't able to go very far. BMW uses a combination of 12 lithium-ion batteries. How to charge this? Well, they use the BMW iCharging station. 240 volts, and it's able to charge these 12 lithium-ion batteries in just 3.5 hours.
Let me show you a small clip of the variable speed limit signs installed on Highway I-285. Then we can have a small discussion about it. Thank you. Variable speed limit signs is a $6 million testing project approved by the Georgia Department of Transportation. It is a technology that uses traffic information, weather information, road construction information, and determines the speed limit on a real-time basis. The physics and electric part of this technology is very simple and interesting too. It has LED light display which illuminates white light and is capable to display numbers from 0 to 99. The entire display controller for this sign is built internally in a cabinet at the back of the sign. These cabinets have security lockout features to prevent unauthorized access. Any tampering to these cabinets can immediately notify the cops. There are multiple power sources for this sign. The right shoulder signs mainly uses the pre-existing power supply from the overhead sign and the underpasses roadways. The combination of existing power supply, wireless communication, and solar power is used for the median signs. The solar power sign have 48-hour backup batteries which are solar rechargeable for cloudy days. The VSL software system is embedded in the Georgia Navigator software, which has a complete vehicle detection data. The Navigator software updates the data every 20 seconds, and the VSL software uses this data to get the average speed every 3 minutes. After every 3 minutes, the VSL sends out two messages. One to display the appropriate speed limit, and second to the dynamic message signs to display reduced speed ahead in case of a sudden speed variation. These speed limits can also be remotely overridden by the TMC but the only possible options provided by the software are 35, 45, 55, and 65 mph in a drop-down menu type interface.
My project is on fuse, so today I'm going to talk about what is fuse, why it is important in our daily life, and what basically it does. So, I have few confusion about it, and I wanted to clear out my confusion. In order to do that, I'm going to investigate on fuse. Basically a fuse is a protector in a circuit. Fuse is not a circuit, it is protector in a circuit. So now I'm going to open my car hood and give you a better understanding and better idea what this fuse is all about. Alright, let's do this. It's a power of physics. Can you believe that without physics we won't be able to do all those things? So,
Javed, रुक जा.
you see my hood is open now, and this is the main box, relay and fuse. They are located here. There's like a small clip on the side, just you can click on it and that box comes up, it opens. And you see there are all various kind of fuses, they all carry different amperages. I took off one of the fuses from the car, and this fuse has three components. Two pins you can see outer pins, and one is in between of these two pins. So basically what that middle pin does, it is connected to these two outer pins, and this enables current to pass through the circuit. And whenever, like as I told you, what fuse is. Fuse is basically in a normal short length of wire which is designed to melt and separate in event of excessive current. So whenever you see that middle wire is separated, basically your fuse is blown out. So you have to replace it in order to enable current into your circuit. How do you know if your fuses are working or not? There are three examples I can show you. Through that you'd be able to know your fuses are not working. First, to your right hand side you can see there's a cigarette lighter. To your left hand side there's a power mirror button, and there's a dome light. If one of them are not working, you can come to your fuse circuit and you can check it out. One of the fuses must have blown out, and you can replace them with new one because fuse works only one. And I hope I gave you a better idea about the fuse. Alright, have a good day.
So it's my birthday, and I'm here with my friends bowling, and I decided to go ahead and start working on my physics project. Who knew that bowling had anything to do with physics, especially magnetism? Well, here I am at Bowmore Lanes, and let's start with the pins. Who knew that the pins actually had magnets in them? On the top of the pins, there's tiny little magnets that attract them to the pin setter.
So let's take a better look at this with this illustration. Not all bowling alleys use this concept of magnetism. This is more common with some of the newer bowling alleys. But, in this case, the pins at the top of the pins contain a magnet, which is attracted to the pin setter. This is the big black device that lowers the pins into place. As it lowers the pins into place, this magnet is attracted to the pin setter. The pin setter lowers the pins onto place onto the alley. As shown here in this illustration by Bowmore.com, as the bowling ball approaches the end of the alley, it passes an infrared sensor. As we know, infrared light lies in the electromagnetic spectrum. Infrared is found between the visible and microwave portions of the electromagnetic spectrum. Upon passing the sensor, a signal is sent to the unit indicating that the conveyor belt should begin. The sweep pushes any remaining pins into the ball pin. A conveyor belt in the ball pin moves the pins under the divider. However, the ball is too large to fit and rolls into the opening side. Another conveyor belt accelerates the ball up a ramp to the top where gravity forces the ball back down and returns it to the next player. While the ball is being returned, the pins fall into another conveyor belt. Again, magnets are used here. Magnets attract the pin into the funnel when the pins are then used to restack back into the next round.
This is our project. We got our electric toy car. It's made up of connects for the body, 2 9-volt batteries, and an electric motor. Here we have the electric motor, which is connected to the 9-volt batteries. in series. You turn it on by pressing it together, and then once it's all set up together, we hook this rubber band to the spindle, and it goes. Alright. So here's our car. We have two 9-volt batteries in series, and then it's connected via these wires with the 9-volt clips to the electric motor, which is good for up to 18 volts, which we have here. Then we use this rubber band connected to the axle that will turn it. We put it over the spindle, which was taken from a spool of a sewing machine. And then when you connect the batteries together, the car goes.
Action!
Here you can see that the wheels have been glued to the axle to allow the rubber band to turn the axle in order to turn the wheels. So we take this rubber band, which is wrapped around the axle, and put it over this spindle from a sewing machine that's attached to the motor in order to create the needed power to turn the axle once the batteries are connected.
Two, three, go. Alright, so this is our car. You see it's rotating. Because of the friction, it's slowing down, I suppose. Alright, go back to him. Alright, perfect. Our circuit, basically that's what's in the car. As you guys can see, this is the series circuit. We got the two 9-volt batteries with actual voltages 8.61 and 8.81 connected in a series circuit, and the resistance of the motor is 2.2 ohms. The current will start from over here and go around. It will enter the negative terminal of the second battery and will go through the resistance and back into the negative of the first battery. So that's it. These are our two series circuits, the theoretical and the actual. In theoretical, we had two 9-volt batteries, so the total volt is 9 plus 9, 18 volt, and the resistance was 2.13 given in our motor. So according to Ohm's law, voltage equals resistance times the current. We got our current to be 8.45 amps. Now, if we look to the actual circuit that we had, our measured voltage for the first battery EMF was 8.61 volt, and the second EMF was 8.81 volt. When we add the two voltage together, we got 17.42 voltage. Now the current is constant in the series circuit, so the current was 2.2 ohms measured in the whole circuit. According to the Ohm's law, V equals IR. Our current in the actual circuit was 7.91. Now when you guys look at the percent error, theoretical minus actual divided by theoretical times 100, our percent error was only 6.4%.